Okay, so we've got recording going, and so let me turn over the floor to Team 5 to share with us their design.
Okay. Um, Hello, everyone. My name is Thomas Stevens, and I'm joined by my teammates Crossman Cruz, Leonardo Fernandez, Joseph Yule, Marty Silverberg, Nathan Tew, and Alan Zoe. Together, we are Team 5, and we are here to present to you the Grobotic Bioincubator. So first, we'll start with a basic outline of our presentation. We'll start with our team's Hedgehog Concept, which was our team's goal for this project. And then we'll do a basic overview of the product and its functionality. Then we'll take a deep dive into our subsystems, going over the functionality, unique features, and the technology readiness levels of each of those subsystems. Then we'll go over our cost projections, and then we'll do a final overview of why you should choose the Grobotic Bioincubator for the next level. And then we'll go into the Q&A portion. Okay, so starting with the Hedgehog Concept. So Hedgehog Concept is crossover of what you're passionate about, what you think you can be the best at, and what drives your economic engine. So every member of our group was really passionate about delivering the best product that we can. We didn't want to deliver something subpar that would just disappoint you. And then what we determined that we think we could be the best at, because we are young engineers, is to be able to research cost-effective solutions. So if we're looking at motors and we find two motors of the same specs, we're going to take the more cost-effective one simply because it gives us better margins. And that ties right into what drives our economic engine there, because driving down cost means more profit, means, you know, make more money. So that leads us to our Hedgehog Concept of creating the most cost-effective product that meets all of the customer needs. And that does not mean that we want it to be the cheapest product, because I feel like the word cheap and being the cheapest product has an inherently negative connotation to it. I mean, because usually when you see something super cheap, it's like, oh, they missed something, you know? So it's like if you're going to shop for a new Honda and you want it to be a little sporty, you could go cheap and get a base model Honda Civic, but it's not going to be as sporty as you want it, and you're going to have to spend a lot of time on the aftermarket, you know, modifying it to make it to the sporty level you want. Or you can go buy a new NSX and pay over $150,000 and get yourself a supercar. Or you can get yourself a Honda Civic Type R for like $30-something thousand and get the fastest front wheel drive car ever made and a capable track car. So we're going to be the Honda Civic Type R of bioincubators. So let's go into a product overview. We're basically trying to reduce the need for human intervention in the process of incubating cultures. So we did this by automating pretty much every part of the process that we could. So the handling of various fluids, the removal of waste, taking of various readings, and even the removal of the tops to our bioreactors. And then this system is capable of creating 8 different culture environments at once, 4 for various size well plates and 4 for conical tubes. It has a programmable user interface that lets the user set various parameters they need for each of those environments. And so we split this system into 5 subsystems, which is the chassis subsystem, the bioreactor subsystem, the liquid handling subsystem, and the liquid transfer subsystem, and the data acquisition and user interface system. I'll clarify this in the beginning. Liquid handling is dispensing of fluids, and liquid transfer is moving the liquid handling system. The names are somewhat confusing. We do regret choosing those names, but just so you know, and don't get them mixed up. All right. And then now we'll go into the customer needs before we go into each subsystem themselves. So the chassis, it sets up the size for the entire system because it is the frame for the entire system. So we did design it to fit onto a lab table, as you can see in this picture right here. That's an actual table that we pulled off of different SolidWorks models that were already available. So that is like a standard lab table. The entire system there is one power source for the entire system that all of the powered parts connect to, and that can be powered by a standard wall outlet. There are no external supports that you need to install. So it's just a standalone thing and it can function on its own. The external temperature will remain under 55 degrees Celsius like you requested. The whole system has a factor of safety of over 1.15. We designed it to be easy to assemble, and we designed it to be accessible to anyone by anyone of normal height. And then going into the bioreactor, we made sure it can incubate for up to 2 weeks like requested. It will run on closed loop control. So basically it'll take the errors in things like temperature and make that the input rather than just a desired temperature. It has the operating temperature of 4 to 70 degrees Celsius like required. It has environmental control for each of the separate, it has 8 different separate environmental control areas. So there's 4 for well plates and 4 for conical tubes, like I stated earlier. It can accommodate all the well plate sizes needed and both of the conical tube sizes needed. It's capable of uniform heating and cooling via Peltier plates. It has a diaphragm that allows the user to capture effluent gases. It is capable of the linear, orbital, and double orbital shaking patterns. It also has a factor of safety of over 1.15. We designed it to be easy to assemble and designed it to be easy to access. Moving on to liquid handling, all the materials that come in contact with cultures and liquids are non-porous and non-reactive. We made sure to follow the BSL-2 lab requirements. We made sure that it can deposit liquids in 1 microliter increments like requested. We have that same diaphragm that is on the bioreactor. It can be accessed through the liquid handling system to input new gases into the system. It is capable of taking optical density and fluorescent intensity readings. It has a laser that is capable of the 1 kilowatt per centimeter squared at 640 nanometers. It can dispense at the rate of 300 microliters, over 300 microliters per second like requested. It is capable of automated waste disposal. And again, it has the factor of safety of 1.15 or higher. It's easy to assemble and it's easy to access. Liquid transfer, which is again what moves the liquid handling system back and forth side to side to line it up. It is designed to be able to process a 384 well plate in a matter of minutes, so it can move quickly rather than having to wait on it slowly move across. We designed it to be modular so you can easily switch out components if you need to. And again, everything connects to the 1 power source on the chassis that connects to a standard wall outlet. And again, factor of safety over 1.15, easy to assemble, easy to access. Onto the user interface, it does have the fail-safes. It will have the fail-safes programmed into it that if there is a culture condition failure, it will notify the user. It has a external emergency stop button like requested. And then it also has different shutoffs if there's improper setup. And we also made sure it was programmable so the user can set the parameters that they want. And again, it has the same factor of safety, the same easy to assemble, same accessibility, easiness. Okay, now going into the chassis. So the purpose of the chassis was to be able to contain all of the subsystems with the exception of the user interface, which is a standalone that will go right in front of it. It will also contain reservoir containers and the power supply unit. And it was designed to be as simple as possible to help offset the detailed designs of the bioreactor and the liquid handling subsystems. Additionally, none of the overall dimensions of the chassis exceed 1 meter, meaning every component and subsystem is easily accessible within arm's reach. The chassis system is comprised of 4 components: the base, which functions as a platform for both the bioreactors and containers; the rail, which serves as the region that accommodates for wiring and tubing with relation to the liquid handling and liquid transfer systems; the housing, which provides space for the gas tanks and the power supply unit; and additionally, the housing and beam function as both support for the liquid handling and liquid transfer systems. Unlike most designs, the chassis is not enclosed. It allows users to freely access everything within the system. We were able to do this because the bioreactors are enclosed by themselves, so we didn't have to enclose the entire system. It's just four main parts that are connected with fasteners, making it easy to assemble or disassemble. And all of the parts are made out of an aluminum alloy, which helps prevent rust and corrosion. Now, going into the bioreactor. So we decided to do two separate bioreactor systems, one that would contain 4 different well plates and one that would contain 4 conical tubes. These designs are identical in function. They both have individual culture control for each of the 8 separate culture environments. They also share a common design in heating and cooling with the use of Peltier plates, providing the thermal needs, so it will heat if it's needed, it'll take heat away if that is needed for each of those environments. So everything can have its own temperature set. So each of those sealed areas will have its own temperature. And then they also share mechanisms for the shaking, the linear, orbital, and double orbital. And the main feature is the ability to maintain each environment independently. So it provides each environment has their own gas inputs, which you see are those black dots right there. Those are the diaphragms for gas input and removal. And it can regulate each temperature on its own for each of them. And each has its own shake pattern as well. The individual control of each environment is a great asset to the operator, as it allows for multiple conditions to be run at any given moment. Each environment is sealed with a borosilicate glass cover, which can be removed automatically with the aid of the liquid handling subsystem. The two designs provide for either 4 well plates or 4 conical tubes, each compatible with multiple size and culturing platforms. A key feature that provides the closed loop control to the operator is the thermocouple. Each culturing environment will have its temperature monitored by the data acquisition system, which can allow the user to increase, decrease, or keep the current temperature at a desired culture environment. Another feature that is key to the bioreactor success is the diaphragm seal that allows the injection of the gas to each environment. This diaphragm is embedded in the borosilicate glass covers. Again, it's that black part you see on there. And that cover each environment. Each environment is sealed by a rubber gasket that's in a trench at the bottom, so you can see it on the left, towards the middle, on the leftmost picture.
Hey, Thomas, it's going to be the next slide, I think.
Okay. Yeah, there we go. It's so sealed using a rubber gasket that's in the trench surrounding the culture area, and these covers are placed by the liquid handling system with the assistance of chamfers that provide minimal effort to seal the environment off. So you can see all those, the thermocouple, the gas diaphragm input, the rubber gasket, and the chamfers on this slide. And now moving on to the liquid handling. The liquid handling system does more than handle liquids. It's a very broad statement, but it has a motorized pipette to aspirate and dispense cultures and media. There's a vacuum suction cup that attaches to the glass covers of the bioreactors to move them while it needs to take measurements and move liquids into the bioreactors. The liquid handling system also manages the optical density and fluorescent intensity readings, because each bioreactor has a mirror lining the bottom so that a laser that comes from the liquid handling system can pass through the culture, bounce off the mirror, and then hit a sensor on the liquid handling system. And then there's also a gas injector that connects to a premixed gas tank that can go into that diaphragm that is on the bioreactor glass cover. And now we'll take a closer look at each of these different subassemblies. So this is the motorized pipette subassembly. On the top left is a top view of the liquid handling system for reference of how these subassemblies fit together. The pipette is a small motor connected to a rack and pinion gear that moves the rubber stopper vertically inside a glass tube. It's very much like a syringe. The glass tube is fitted with a pipette tip adapter where a smaller motor opens and closes a mechanical iris that can pick up and discard pipette tips. So for each time it is moving liquids, it uses a new pipette tip. This is to prevent cross-contamination. And then next is the vacuum suction cup. The suction cup is connected by a pipe fitting to a miniature air compressor so that the cup can attach and release the glass covers. The suction is moved vertically by a linear cam, a motor spins a pear-shaped cam that pushes on a ball bearing that is connected to the suction cup and a guide rail. As the cam reaches its long end, the bearing and cup moves downwards. The spring assures that the bearing is always in contact with the cam as well and pushes the suction cup back upwards. Next is the gas injector, which has the same type of assembly to move the nozzle. And so that will be connected to a premixed gas container that and then it will be inserted into that diaphragm that's on the glass cover, and it will allow the user to inject whatever gas combinations they need. And next are the optical density and fluorescent intensity readers. They both use lasers to take a measurement. The optical density laser is at an angle smaller than 90 degrees, so the reflected beam can hit the diode for a reading. The fluorescent intensity laser is pointed horizontally at a filter cube. We used a filter cube instead of a monochromator for the fluorescent intensity readings because monochromators are way more expensive. So that goes back to our Hedgehog concept, where we're trying to make a cost-effective solution rather than the most expensive and out-of-this-world solution. Some of the key features of the liquid handling system is the fact that the optical density and fluorescent intensity readers are conducted by the system, means the underside of the bioreactors can be more compact, and basically it helps save space. The suction cup and gas nozzle are retractable, so they're not in the way while other liquids are being transported. And the mechanical iris that holds the pipette tip allows for pipettes to be discarded and prevents cross-contamination rather than having to take off each pipette tip, disinfect it, and then reinstall it. And so now we'll go into the liquid transfer subsystem. So the liquid transfer subsystem is designed to move the liquid handling subsystem. Again, our naming wasn't the best for this. In the future, we'll probably have to change the names. And so it will move across the surface of the chassis to a desired height to be able to interface and manipulate the 4 culture plates and tubes of the bioreactor system. The liquid transfer system uses 2 carriages mounted on rails to move across the chassis surface, using motorized wheels for motion. To adjust the height of the carriage, 2 motorized lead screws are mounted to one side of the chassis, and rotation of the lead screws allows for the carriage to change its vertical position. The other side of the chassis has guide rails to act as stabilizers for this carriage. The liquid transfer system was designed to be mechanically simple and easily accessible. The carriages only require 4 square motors and a wheel for full assembly, and the rails only need to be threaded into their respective housings. The entire carriage assembly is made of lightweight aluminum. That way it can be easily taken on and off for desired adjustments. Now moving on to the data acquisition and user interface system. The data acquisition and user interface serves to both monitor and control the process. The overall design is very simple and user-friendly, as it only consists of 3 off-the-shelf parts that can be quickly familiarized. Additionally, the system is fairly small and doesn't need to be mounted to the chassis. It can stand on its own, which allows the user to basically move it to wherever they want it. So it creates more accessibility because it's not in one set spot. It can be wherever the user wants it. As mentioned before, it only consists of 3 off-the-shelf parts. The manual switch serves as a way to shut off the entire system when necessary if there's an emergency. So it doesn't require the user to go into the user interface and find some menu to shut it off. It's just one button, you hit it when you need to. And then the light fixture serves as a visual indicator of the system status. The user interface device itself is a touch screen, and it's where the user will be able to monitor and provide inputs into the system. Since it is just going to be an off-the-shelf touchscreen, it's going to be fairly easy for the users to navigate because most people are familiar with using touchscreens at this point. And then it has multiple ports that connect to different components in the system. So some of the key features of the data acquisition and user interface system: the whole system costs less than $100 and each part can be easily replaced. The data acquisition system, as well as the manual switch, can be carried by hand, making the system both accessible and versatile. Lastly, the system itself is within an acrylic case, protecting the device from any reactions caused by chemical mishaps. So now we're going to go into the technology readiness of each of these subsystems. So as you can see on here, there's a scale from levels 1 through 9 of technology readiness. 9 is the highest, meaning the technology can be rolled out this second. And then 1's the lowest, meaning barely basic research has been done into this technology. So starting with the chassis, as you can see, the chassis scores a 5 out of 9. This was given this level because there's not really new technology being utilized for the system. It's a structure. So that technology has existed since the beginning of time. The only reason it doesn't score higher is because this exact assembly has not been prototyped yet. And so we can't really give it higher without there being a real prototype yet. Moving on to the bioreactor, this scores a technology readiness of 3 out of 9. This is due to the research being done to show that this can work. The only reason why it wasn't given a higher score is because there's not really similar designs on the market that we can judge technology development from. Basically just using the way our cap system work is very unique to our design. And since we haven't done much prototyping, we can't judge the technology development beyond this level. The liquid handling system also has a technology readiness of 3 out of 9, and that's due to it combining multiple different technologies that we haven't really seen be used together. Because if it was just a rack and pinion syringe, it would score higher. If it was just an optical density and fluorescent intensity readings, it would score higher. If it was just a way to transfer gases, it would score higher. But since it's a combination of all of those things, we don't feel like we could give it a higher score until we hit that prototyping phase. Moving to the liquid transfer system, this one also scores a 5 out of 9. That is, again, due to there being very similar technology out there exists because it's motors driving wheels on a track, essentially. And again, similar to the chassis, the reason why we didn't score higher is because although the technology exists, we know it's going to work. We just haven't prototyped this exact orientation yet, and so we can't justify it being higher. Moving on to the data acquisition and user interface, this scores a level of 7 out of 9. That's because it's completely of off-the-shelf parts. So we know it works because we're buying it from somebody who made it work. The only reason why it doesn't score an 8 or a perfect 9 out of 9 is because the specific code that will be programmed into this interface has not been developed yet. So now we're going to go into our cost overview. So to start off, we estimate our OTS parts to cost us $5,406.22. This makes up the vast bulk of our costs because we tried to include as many off-the-shelf parts as we could. This cost also includes some custom parts that we plan on getting directly from manufacturers rather than manufacturing ourselves, because we determined that it'd be simpler to do that. Next is the raw materials of parts we plan to manufacture ourselves. This is primarily lots of metals and some different polymers as well. This comes at $1,774.20, and the cost to manufacture those parts is currently estimated at $750. We're currently putting the cost to assemble the entire system, as in like putting everything together at the end, at $350. So this puts us at a total estimated cost of $8,280.42, which puts us roughly 17% under the total budget given by the customer needs. So this gives us a large margin of error when it comes to future unexpected costs that will probably come up in the prototyping phase. And this also allows for higher profit in the future. So moving on. To summarize, why should you choose us? There are multiple reasons to choose the Growbotic Bio Incubator. First off, we met every customer need provided to us. We didn't skip over any of the provided needs and then try to create some argument of how it was better this way. You gave us the needs, we met the needs. Also, we remained well within the provided budget, meaning there's that room for error for unexpected costs down the line, and it allows for more profit in the future as well. Another reason is because we made our design not overly complex. We didn't make it so we have all these cuts to make it as lightweight as possible. We made it so it can be easily manufactured. This means in EML4502, the student should have a relatively easy time prototyping it in terms of we didn't make it so a student can't manufacture it. And then lastly, the last reason you should choose us is because of us. We're willing to continue working on this project and willing to keep helping and make sure this project meets to the end and keeps going and is successful. And so that concludes the presentation portion of this section. Thank you for listening to me for this almost 30 minutes. And then if you need to email us with any additional questions, we have our emails there. If not, I'm gonna open up for the Q&A portion of the presentation. So if there's any questions, let's hear them.
Okay. Thanks, guys, for giving us a great presentation. You did an excellent job. Let us, as you suggested, open the floor to our panel for questions. And if there are none immediately,
Oh, I've got plenty.
Oh, okay. Go ahead.
I was just waiting a second before I said anything. Cool. First thing is just a general presentation thing that I've seen a couple of times now, and it's gotten to a point where it's made me angry. So you guys get to have my statement here. Multiple slides was just a wall of text. It is literally the single most boring, atrocious thing I can be staring at, where you read off bullet points that are 4 lines long, and it's just text on a page. That's a personal rant, but it goes against everything that is fundamental for giving a good presentation. And our professional communication classes failed you, and I'm sorry for them, and I'm sorry for you having been failed in that way. But just try to avoid lengthy bullet points and walls of text. It's painful for everybody. For you reading off the slides, for us watching your presentation, across the board. On the actual technical things, those borosilicate covers for the tubes and the well plates, how do those get made?
So the idea was to cast them. So that was our original idea, and that's kind of what we're going with right now.
All right, how high of a temperature do you need to get borosilicate glass or get sand to in order to be able to turn it into borosilicate glass and cast it?
Probably very high.
Yeah. Do we have the capacity to do that?
So
lab?
the idea with those was we were going to buy them from a manufacturer.
Okay.
So give them our drawing and then have them manufacture.
Did you account for molding costs for getting castings done in your total cost?
We've estimated it, but I'm sure it's probably going to be a little bit higher than what we're thinking.
Okay. All right. And my second thing is the rubber gasket seals you have down underneath those covers.
Correct.
What makes it seal?
So we have when we have the plunger on the liquid handling pushed down on the glass cover, we're at the same time we're going to be drawing effluent gas or any air out to try and create a seal. So we're using gravity and a slight negative pressure in there to create that seal.
Okay. But then once I'm done with messing with the effluent gas and everything like that, and I just let it sit, is it going to remain at a slight negative pressure?
No. So we're going to have we're going to have to inject some gas in there. So at the user's desire of what gas needs to go in there and at what volume.
Okay. So once you have it back at normal pressure, what's going to make sure that it stays sealed? And then I don't have my effluent gas that's being generated by my bacterial culture leaking out into my ambient environment. Like in order for that gasket to seal, it needs to be compressed. And once it's just sitting there and the cells are doing their thing, I don't see how, besides gravity. And the question is gravity enough to compress that seal?
That's a good question. We haven't done that much research into it, but the idea was to use gravity to keep it there.
All right, yeah. So look into it. Does the mass of that compress my rubber gasket enough that I would say it seals?
Okay.
And as you're asking, sorry to interrupt here, maybe I didn't get this when we were going through the design reviews and stuff, but I'm trying to draw here and I'm not doing a very good job. But um, my impression, maybe I misunderstood, was that it wasn't just like a gasket that something would just sit on, but you guys actually had like a U-shaped channel that had. I'm trying.
Yes, there is a channel in there. If you can go back a couple of slides to the bioreactor, maybe we can explain this a little bit better.
So in other words, again, I haven't drawn this super well, but it's you're actually, by pushing the cover in. Oh, okay.
Yeah, but just the gasket's flat on the bottom. If this thing
Okay.
had a groove like right here on the side where I'm drawing,
Yeah.
and then you put the O-ring right here, and when you press the glass down in there, it squishes the O-ring to seal it.
Okay.
I believe it. But in this current configuration, I'm just like, well, that's not going to seal.
Yeah. Okay. I must have missed that. I was always under the impression that it was the way that I drawn it here, but now I see this in cross section. I was wrong. So, okay.
And then could you go forward to the liquid? I think it was the liquid transfer system slides. Yeah, this guy. You got this wheel on a rod. Two questions here.
Right.
One, how much do those rails displace and deform due to motion along their length, motion of the carriage along its lengths?
You mean from bending?
I mean, from the weight of this thing hanging on to them, how much do they bend and deflect downward?
Oh, we did the FA analysis, and it was under like 0.1 millimeters.
What are those rods made out of?
They're made of aluminum.
What's their diameter?
7 millimeters. They're solid. They're not hollow.
You said under 0.1 millimeters?
Yes.
All right. I'm skeptical.
21 millimeters.
Incredibly skeptical, unless this liquid handling system here weighs close to nothing.
That's
with
like
all the motors and everything on it. I'm just, I'm skeptical of it. So yeah, and then my other thing is with these pulleys that are going on those rails, what's the coefficient of friction of these pulleys on those rails? How are you going to make sure that they're actually translating and moving and not just slipping and spinning in place?
Right. I could put some rubber grooves on there to improve the traction.
I'm not saying, so the bigger thing here isn't to just add something onto it to make it better traction. It's, are there other things that could be used that are better than a pulley with a groove on a round rail? So the concept is fundamentally sound. It's just missing that next step of what are the things that could go wrong with this, and how can I design it to account for those mishaps?
I see, right. The only issue that I can think of is wheel slip and traction issues.
Right.
Right.
And so there's plenty of methods that have been developed for handling gantry style motion without slip. So
can you guys can you guys show yeah, I was Dr. Nemi and I were, oh, actually, hang on. Ryan Garcia has a question in the chat here. We'll get back to my question in a second. He wants to know, how are you making the frame for the liquid transfer system? Is it made from a solid billet?
So Ryan, you're talking this whole thing here?
Do you mean the carriage? Yeah, the carriages are supposed to be cast and then machined.
So yeah, my question was, is it the big rectangle piece? Is it one solid piece, or are you joining them together somehow?
Yeah, it's one solid piece.
Okay, with
But
all the
it's-
space machined out.
So
Right.
it's cast, it's apparently, so they were saying it's cast close to nominal and then machined.
Right.
Okay.
Sammy, you look like you're having thoughts.
I would reconsider that answer that was just given. Doesn't seem feasible or price smart to cast that part there.
I believe it'd be better to get a billet of
seems-
near nominal size than machine rather than cast. You can find plates of sheets of aluminum of similar size.
Or make it out of a bunch of bars and bolt them together.
Seems like it can be assembled. Yeah.
Right.
It doesn't seem
Yeah,
like
it's-
there's any particular. It doesn't seem like there's any particular advantages to having it one solid piece as opposed to.
You can actually just water jet this thing out and then machine it a little bit
Okay.
instead of casting it. But
So that if I could jump back in, the thing that I actually wanted Dr. Nimi to see, because I like it, but I'm not a dynamics, mechanics, tribology guy, was that your iris solution for picking up the pipettes. Like, I thought that was pretty clever, but maybe if you guys could explain that. Yeah, there it is. If you could explain it a bit more, and then I'd love Dr. Nimi to chime in on that and tell us what he thinks, because like I said, I liked it, but this isn't my area.
All right, so the picture doesn't do it much justice. It hangs a little further below the bottom plate of liquid handling, but it's one part, the bottom and the little cylinder of the mechanical iris is all one part. Each fin of the iris is individual, and it has a pin that sits in those small circles that you see in that picture, the front end picture of the iris.
so it has a pin that sits in each one of those that I just circled.
Yes.
Okay.
And then in the top picture, the bevel gear on the bottom is the same part that has tracks for those fins. So when it rotates, it opens and closes the iris like a camera.
Yep.
If that makes sense.
Yep.
And then that bevel gear, 90 degrees with another bevel gear and a small motor that opens and closes. That would spin, which would open and close the iris. And then it closes on a pipette tip to hold it and then releases to drop it off to discard it.
Is the iris custom made using all custom parts?
It would have to be, yes.
Yeah. So my statement on this is that is a really cool concept. I would love to just make all these parts and give them to you so you can see just how much of a nightmare it's going to be to make. Like a nightmare of manufacturability is an understatement here. It's genius. I'm not sure how well it would. So you're saying you're going to pick up like a micropipette tip?
Yeah, it would be a 5mm pipette, which are kind of hefty. They're kind of big.
A 5 milliliter pipette?
Milliliter, yeah.
Okay. And then you'd be sucking, and then like that plunger up here is what would suck fluid up into it and stuff when you pick it up?
Yeah.
Okay. So my concern would be slipping vertically when that plunger is actuating. I don't see a good way of, beyond just the friction of it, to hold that pipette tip from you're holding it around the circumference. So my concern there would be slipping of the pipette tip from a mechanical standpoint. But I mean, that's cool as hell.
Thank
I just my statement on making it is good luck.
Yeah.
Um,
I try to make it as easy as possible so the fins are the same thickness as the thickness of the wall in which they sit in. So if you just line them up on the wall, it should all like fit in. But they're also small, so it would be still
Yeah,
be a
it's-
nightmare.
it's you're going to be assembling this thing with like tweezers and a monocle. Like,
Yeah.
I mean, it's like I said, it is really cool, and I am. Did you guys did you do any like kinematics analysis on this to like get a how much it would need to rotate to open and close certain amounts and all that?
I didn't do a full analysis, but from just doing the SolidWorks, you can see that it's less than
Okay.
like a 90-degree turn to fully open and close. Mostly because it doesn't have to close all the way. It only needs to close up to the
So, yeah.
where the pipette would sit.
It's I guess it's really cool. It's just needlessly complicated, but really cool.
Thank
All right. So we might have time for like one more question. We're right at 1:30. But if there was one more quick question, we could probably field it. Seems like no. Okay. So in that case, let me stop recording.